Water repellency and resistance to water penetration. One of the major functions of feathers is to prevent water from reaching the skin or weighing down the remiges and tail feathers in flight. With very few exceptions, all birds benefit from a plumage that optimally repels and resists the penetration of water. However, the manner in which this optimum is realized for each seabird family is closely associated with its behavior and interaction with its habitat and, as a result, the feather characters responsible for water repellency and resistance vary accordingly. To understand the way a water repellent/resistant structure functions, certain aspects of surface physics should be made clear. The water repellency of feathers and other biological porous structures, such as the stomatal apparatus of leaves and the spiracles of insects, is governed by the fundamental principles of surface physics that apply to all porous surfaces whether natural or man-made. It is determined by the relative areas of solid water and air-water interface and their respective interfacial energies regardless of the actual architecture of the repellent structure itself. If the surface of the solid is coated with another material, such as paint or preening oil, it will assume the properties of the coating material. For feathers coated with uropygial gland oil, the feather-water interface is, in fact, an interface between gland oil and water. When a drop of water is placed on a smooth feather surface such as the rachis, it will curl up and roll off easily. The surface is then said to be water repellent, the actual extent of which is determined by the contact angle theta, defined as the angle between the tangent to the curved water surface at the point of contact with the solid surface and the plane of the surface on which the drop is resting, measured through the water. When the drop is placed on the porous vein of the feather, it will entrap air in the hollows and interstices, forming additional air-water interfaces, which will cause considerable increase in the contact angle, according to where F1 is the area of solid water interface and F2 is the area of the air-water interface per unit of apparent surface area. For water drops on barbs, F1 and F2 can be expressed as and where 2 represents the diameter of the rami measured in the plane of the long axis of the rami separated by distance 2d. Note that the increase in apparent contact angle is ascertained only by the parameter, r plus d/ran, not by the separate values of ran d. Thus, theta a for values of this parameter ranging between 2.4, penguins, Sphenicidae, and 10, land birds, would vary between about 126 degrees and 154 degrees, roughly correct by experimental verification. These values are significantly higher than those attained for the most repellent of smooth surfaces, which equal about 114 degrees. 1. Has been derived solely from basic physico-chemical principles without reference to parameters pertaining to any specific dimensions of the porous surface. In addition, the values of F1 and F2 are determined only by the areas of solid-liquid and air-liquid interface per unit of macroscopic surface areas without dictating the shape, curvature or configuration of these interfaces. Therefore, the relationship between the dimensions of a porous surface provided in terms of F1 and F2 and its ensuing contact angle as represented by 1, is a rigorous one, not an empirical one, and is of general validity. 1. Has been tested experimentally and was found to be correct by Cassie and Baxter and Rauke using paraffinated stainless steel wire cages and grids. For these particular models, calculations for the values of F1 and F2 could be made according to EECS 2a, and 2b. Many other studies including recent ones have reported contact angle measurements on porous substrates including feathers and consistently confirmed the correctness of the above premises. In order to measure contact angles on smooth or porous surfaces correctly, certain experimental conditions have to be met, such as, the drop has to be small enough so as not to be perturbed by gravitational forces, but large enough to cover a representative area of the porous surface. The drop should be prevented from evaporation, which would turn the advancing contact angle into a receding one. Feather specimens should be covered with fresh preening oil, not rinsed with an ethanol wash. When these conditions are met, the correct contact angle is usually found to be within 1 degree error as observed by multiple authors. These results have shown conclusively that contact angles can be reliably calculated from and represented by the dimensions of the porous surface alone. An expression for the pressure, P, required to force water between the rami and barbules, can be derived from similar premises and reads. Here, gamma represents the surface tension of the water. This equation shows PTO be inversely proportional to Rand, R plus D/R. As a result, the requirement of relatively large values for R plus D/Rho provide sufficient water repellency is opposed by the need for small values for this parameter to attain good resistance to water penetration. Thus, the structural characteristics compatible with optimal water repellency are, at least in part, in conflict with the requirements of resistance to water penetration. This conflict has important implications for seabirds, which must realize a balance between these two opposing functions to cope with their respective habitats and behavioral patterns, as indeed they do. Experimental data on water repellency and resistance to water penetration for double-crested cormorants, Phyllacrocorax ortus, and Anhingidae, have shown that results can be satisfactorily interpreted in terms of ramus diameter and spacing only without recourse to barbules. There, R plus D/R values for barbules are in the approximate range of 4.5 to 5.5 as found for almost all bird families regardless of their feeding habits or interaction with open water. This suggests that the contribution of barbules to water resistance is real, but not based on the same mechanism as applies to rami. Barbules provide an interlocking mechanism by preventing the rami from separating under the increasing water pressure while increasing their own separation by their hooks sliding in the flanges, a process that can be verified under a low-powered light microscope. Similarly, water drops being repelled by the rami and not involving the barbules can be observed with a magnifying glass. The contact angle theta of water drops on smooth feather surfaces, such as the rockies or on a microscopic slide covered with preening oil, measures about 90 degrees as established by various authors. The same value was found for water drops on polyethylene foil, and this is no coincidence. Polyethylene almost exclusively consists of methylene groups, C.H2, which are the predominant chemical component of preening oil. Note that when theta is 90 degrees, cos theta equals 0 and sin theta equals 1, which reduces 1 to cos theta at equals minus f2 and 2b to f2 equals 1, r/r plus d. These fortuitous circumstances allow the investigator to determine the apparent contact angle from the value of R plus D/R alone. For instance, Cassie and Baxter found R plus D/R for their duck feathers to be 5.9, which corresponds to a theta A of 147 degrees in good agreement with their experimental value of 150 degrees. These results, corroborated by other workers, have shown that for feathers coated with fresh preening oil, both the water repellency in terms of the apparent contact angle theta A and the balance between water repellency and resistance expressed by the value of R plus D/R, can be correctly predicted from the microstructure of the feather alone. Furthermore, the value of 5.9 for duck feathers, when compared with 4.8 for the white-breasted cormorant, Phyllacrocorax carbo, and 7.1 for the European starling, Sturnus vulgaris, suggests that the duck, and probably all dabblers, are more water repellent than cormorants, but less so than starlings. On the other hand, cormorants show a superior resistance to water penetration, particularly when compared with starlings. Measurements on more than 160 species of about 45 bird families have shown that R plus D/R values vary from about 2.3 for penguins to about 6.5 for gulls, laridae, and up to 10 for most terrestrial birds, Table 1. This range in values for this parameter suggests that each seabird family, and indeed each water bird family, has evolved a balance between water repellency and resistance to water penetration that suits its particular habitat and behavioral pattern. Summary of seabird families and species: barb diameter, 2R, and R plus D/R values of contour feathers, habitat/behavior. The data on barb diameter, spacing, and R plus D/R values published in the peer-reviewed literature are far from a complete inventory of bird plumage, but on the basis of what is available, the following observations can be made and tentative conclusions reached. First, the distal one-third of breast, abdominal, and back feathers shows the pattern structure that confers the water repellency and resistance to penetration. The proximal and medial parts show no such structure. The tail feathers and remiges, on the other hand, are structured over essentially the entire length of the feather and have values of R plus D/hat are generally small, which prevent these feathers from becoming waterlogged. Among water bird families, contour feathers vary more in values of R plus D/R, which range from 2 to 10, than rectrices and remiges, both of which vary little and range from 2 to 4.